Hi, welcome to this week's recitation. Today I will discuss some recommended exercises in section 5.2. A basis must be a linearly independent set. Therefore, for this exercise, you just need to check whether the reduced row echelon form of this matrix has a zero row or not. So this exercise is similar to example 2. These three exercises are similar to example 7, so we will not do them here. For this exercise, just find the general solution of ax equals to 0. Then you are done. The independence calculation here means that you need to multiply a by the element in the basis you found and make sure it's 0. Find the general solutions of ax equal to 0. For this problem, you need to make sure L is injective and surjective. Since it's a little bit troublesome, so here I will just give you some hints, and please do the rest by yourself. To show that L is injective, that P1 of t is equal to A0 plus A1 times t plus all the way to an times t to the nth of power, t to the power of n, and P2 of t, which is equal to B0 plus B1 times t plus all the way to Bn times t to the power of n. Then you need to show that if L of P1 of t is equal to L of P2 of t, then P1 of t is equal to P2 of t. Here, if you want to show that L is surjective, then you need to show that for O P2 of t, which equals to P0 plus P1 times t plus all the way to Bm times t to the power of n, there exists an P1 of t in Pn such that L of P1 of t is equal to P2 of t. The rest is left to you, so please do the rest by yourself. For this exercise, for this kind of problems, you can just take the coefficients of those polynomials as vectors, and you collect those vectors as a matrix. Then you can find a basis by similar methods in previous problems. Similar to example 6. For this exercise, if you can show that the degrees of p, p prime, all the way to the nth derivative of n are n, n minus 1, all the way to 0, then by an exercise we have done before, this set is a basis of Pn. I recommend you to review exercise 2.4.24. These two are easy exercises, so I will leave them to you. This one is similar to example 17, so I will not talk about it here. It's similar to example 17 in the textbook. And this one is similar to example 13, so again, I will leave it to you. Similar to example 13. For these three exercises, you can use theorem 5.2.11 and theorem 5.2.12 to solve them. Use theorem 5.2.11 and theorem 5.2.12 in the lecture notes. First, we find the dimension of R m by n. Here we list a basis of R m by n. Here we collect some m by n matrix such that the ijth entries is 1 if I is equal to S and J is equal to T, and the ijth entries of A is 0 otherwise. And S and T is in 1 to n and 1 to n. T is less than and equal to n. And this is a basis of R m by n. This set collects all the matrices such that all entries are 0 except a 1 at some position. Since there are m times n different matrices. In this set, the dimension of R m times n is equal to m times n. Here also we list a basis of such spots. Here we list a basis of such subspace. Also, we collect some matrix in R m by n, and the ijth entry of A is equal to the jith matrix of A. If I is S and J is T, then the ijth entries of A is equal to 1. Otherwise, it's 0. For O, 1 less than or equal to S, less than or equal to T, less than or equal to 2n. AJ, oh sorry, yes, AJI. Is a basis of this subspace. And you can check that there are n times n plus 1 over 2 different matrices in this set. So the dimension of this subspace is n times n plus 1 over 2. This exercise is also related to an exercise we have done before. You can just use exercise 5.1.27 to solve this problem. You can use exercise 5.1.27. Similarly, here we find a basis of phi. We let S be a basis of the null space of B. Here we know that. The number of elements of S is equal to the nullity of B. With this, we can write the basis of V as A is a matrix, and little a is a column of capital A. A is an m by m matrix, and the ith column of A is in S if I is equal to T and is equal to a 0 vector if I is not equal to T. And this is a basis of V. Then the dimension of V is, since there are m columns and each columns have this many options, so the dimension of V is m times the nullity of B. Exercise 39 is an easy exercise, so I will not do it here. Okay, first we let V be this vector space, and we collect U1, U2 to UK, and so on as capital U. U1, U2, and so on to UK and to infinity. Here, you need to show that you have two things you need to show. First, you need to show that U is linearly independent. And the second thing is you need to show that span of U is equal to V. Since they are not difficult, so they will be left to you. But here I will give you a hint. When we talk about the definition of linear combination, any linear combination contains only finitely many terms. And that's exercise 43. Okay. We left the part. For exercise 37, I will not show that it's a vector space here, so please show that please show that V is a vector space on your own time. Exercises 53 and 54 can be easily proven by method of contradiction, so I will not do them here. Use method of contradiction. For this exercise, you can just use theorem 2.4.10 to solve it. And for the next exercise, you can use theorem 5.2.11. Theorem 5.2.6 states that for a finite dimensional vector space, every basis contains the same number of elements. Since the dimension of Rm is m, by this theorem, if the columns form a basis of Rm, then m is equal to n. Since the dimension of Rm is equal to n, by theorem 5.2.6, n is equal to m. The dimension of the range is always wait a second. Okay, the dimension of the range is always less than or equal to the dimension of the domain. So the answer to this exercise is no. For more detail, you can find theorem 5.2.14. Here we start from letting x, y, and u be elements of capital X. Here we check whether the three conditions hold. First, we check the reflexive property. Since x minus x is equal to 0, and of course 0 is an element of u, so the reflexive property holds. Secondly, we check the symmetric property. If x minus y is an element of u, then y minus x is equal to minus x minus u. And since u is a subspace, so minus x minus u is also an element of u. So the symmetric property holds. Lastly, we check the transitive property. If x minus y is an element of U, and y minus U is also an element of capital U, then now we need to check whether x minus U is also an element of U. Since we can rewrite x minus U as x minus y plus y minus U, since those two elements, since these two are both elements of U, and U is a subspace, so this term is also an element of U. And this shows the transitive property also holds. Since all three conditions are satisfied, it is an equivalence relation on X. Here we first observe the rule by observing the rule. We can see that once xi and xi minus 1 are determined, the whole sequence is determined. Therefore, the subspace can be spanned by the linearly independent set xi minus 1 is equal to a and xi is equal to 0. Or xi minus 1 is equal to 0, xi is equal to b. Know that a and b are both not 0. So the dimension this subspace is 2. For this exercise, we will use method of contradiction. We let V be the vector in capital V such that we let little v be the vector in capital V which has a unique expression as a linear combination of vectors in capital S. Suppose S is linearly independent, then 0, the 0 vector can be expressed in at least 2 different ways of a linear combinations of vectors in capital S. Oh, sorry, this is linearly dependent set, not independent set. Since S is linearly dependent, so there is a trivial relation of 0 and a non-trivial relation of 0. So 0 can be expressed in at least 2 different ways of linear combinations of vectors in S. Since 0 have 2 different expressions, and since V is equal to V plus 0, V also has at least 2 different expressions as linear combination of vectors in capital S. But we have assumed that V has a unique expression, so this is a contradiction. This one is similar to, sorry. Okay. This one is similar to the previous exercise, so I will leave it to you. Here we have two cases. If V spans W, then any linearly independent set then any linearly independent set can have at most 7 elements by Theorem 2.4 to 2.10. So in this case, U cannot be linearly independent. Since this case is impossible, so the only possibility is U spans W, and V is linearly independent. Now we find the dimension of W. Since we have U spans W and W is linearly independent, if U spans W, then by Theorem 5.2.11, dimension of W is less than or equal to 8. And since U is linearly independent, by Theorem 5.2.12, seven is less than or equal to the dimension of W. Now we combine these two, so we have dimension of W is equal to 7 or 8. Okay, first we suppose that x1, x2, and so on to xn is linearly dependent, and we have a non-trivial relation. Here, alpha I is a real number, and not all alpha I are zero. Then here we have T of, we put this into T, and we have and since T is a linear map, so you can rewrite this into the summation of alpha I, yi. And since a linear transformation maps a zero vector into a zero vector, so this is 0. And we have a contradiction. By the above argument, if we want x1 to xn be a linearly independent set, y1 to yn is not necessary, need to be a basis. X1 to xn is linearly independent as long as y1 to yn is linearly independent. So we can see that as long as y1 y2 and so on to yn is a linearly independent set, then xy, x2 all the way to xn is linearly dependent. Okay, here we let A be a matrix. And if X is in the column space of A transpose, then there exists a Y such that A transpose times Y is equal to X. Here we take the transpose of both sides of this equation, and we have the transpose of X is equal to Y transpose times A. Now we assume if X is also in the kernel is in kernel of A, then we have AX is equal to 0. Therefore, we have, if we multiply X by itself, and X transpose is equal to Y transpose times A, and times X. Since X is in kernel of A, so here is 0. So this is equal to 0. And this implies that X is a 0 vector. Actually, this exercise has many different ways to solve it. So I encourage you to find at least 2 different ways to prove this problem. Here we start from the equation AX equals B is consistent for O, B in Rn, and this is logical equivalent to the column space of A is equal to Rn, and we know that the dimension of Rn is equal to n. Here we take the transpose of A, so we can rewrite this into the row space of A transpose. Now here we apply the Recognitive Theorem. Since the dimension of the row space of the transpose of A is n, so the dimension of the kernel of A transpose is equal to n minus n, which is 0. Here we use Recognitive Theorem. And if the dimension of the kernel of a matrix is 0, then it contains only 0 vectors. So that's exercise 88. Is there any questions? Then we are kind of done here. Then that's this week's recitation, and I'll see you next week.